Those extra sums, I could make additional nodes for them if I want to, but there's no real reason to it because I already have a table that includes all of those arguments. And so I'm just summing out larger fractions of that table instead of, right, I can sum out several variables at once from that table with a nested loop, right? And I don't actually need to create any new piece of my data structure to contain the result because I'm just going to multiply it into something later. All right, so that was our example, so I should point out also that we could do the same junction tree in a slightly different order, right? So if we did, like I mentioned, more than one variable elimination order can correspond to the same junction tree. And so this is the reverse of the order that I considered on the last slide. And if you look at it, right, so you'll eliminate F, which means you'll do BDF as your first clique, right? And then you eliminate D, which adds A, right? And so you'll have A, B, D as your next clique. Right, then you eliminate B, which adds E as a neighbor, A, B, E, right? And then you eliminate A, which adds C as a neighbor, right? Which is, I guess, A, B, and C, right? And we can connect these nodes, it'll turn out, in either of the ways, right? We could connect it either in a line or in a tree, right? So let's just do the line for convenience, right? And so this is exactly the same as one of the junction trees that we built on the other slide. But the interesting thing, right, is that we're going in the opposite direction across each edge, right? So before, when we went down the junction tree, when we went this order, right, when we went from the bottom to the top of the junction tree, we summed out C from a clique containing A, B, and C, and we got a table over A and B that was the result, and that table was passed on to this clique right here, right? But if we go down from the top, right, we'll do some summing, we'll get to a clique over A, B, and E, we'll sum out E and pass a message across that's a table over A and B down to this node, right? So for each of these edges, we could pass a message in either direction across it, and it would lead to the same junction tree, okay? So that's just kind of interesting. I guess the maybe even more interesting thing, well, actually, let's get to that later. So I think I said this before, but I wanted to put it up on a slide, right? So the formal definition of a message is just a smaller table that we create by summing out some variables over a factor, right? So we have a clique in our clique tree. We sum out some of the variables. We get a table over fewer arguments, and that's a message. And we'll take this message, and we'll later multiply it into exactly one other clique, right? And there's going to be one message per edge. It could go in either direction over the edge, right? And the arguments of the message, if you look at the junction tree, right, if the arguments of the message are always going to wind up being, right, so if we look at the message that goes between these two guys, it was a table over A and B. And in general, if you have some set here, the intersection of those two sets is what's going to be the arguments of the message that go across. So you can label every edge of the junction tree with the arguments of the message that go across it, right? And the name for that is called a separating set, or a sep set, right? And the idea is it's called separating because once you know the message, you don't need to bother about the whole factor on the other side, right? So yeah. The other interesting thing is if you think about it, suppose that you fix a junction tree and fix an edge in that junction tree and consider a bunch of different elimination orders that are consistent with that junction tree and that use the edge in the desired direction, right? So what's going to happen before we pass the message, right? We'll sum out all of the variables that are mentioned only on, let's say, the right side of the tree, right? and we'll get down to a table that's just across the message, right? And it doesn't really matter what order we sum out those variables. You can see that we're going to get the same message no matter what, right? Because it's the same expression, we've just moved one sum in first or a different one, and we get the result at the end is just this message. So fixing a junction tree, there's going to be one message that you could pass over an edge in that direction, and one message that you could pass over an edge in the other direction. So there's just going to be two possible messages for every edge. No matter, there could be exponentially many possible elimination orders that we could use, but with our junction tree, we can get any one of those orders by only a small collection of messages, one message per edge. Okay? So that's kind of surprising, interesting, useful, right? So it's a good thing to know. Yeah. So if you're summing out from this side of the tree, right, you're summing out these variables first, and you'll get a message that you could pass in that direction. So you take the same edge, there's the other side of the tree. If your elimination order starts from over here, you're summing out this side of the tree and passing a message in that direction, right? And those don't have to be the same message. They have the same argument set, but they don't have to be the same message.
This is when you're talking about the entire tree, not just one edge.
Right, a message only makes sense when you're talking about the entire tree, right? So an elimination order is something for the entire tree. We're eliminating the variables in some order. That order has to start over here or over here. If it starts over here, you're going to have to sum out every variable over here before you get to this edge. And so you'll get a message that goes over this edge. If you start over here, you're going to have to sum out every variable that's over here first before you wind up getting a message that goes across that edge, right? And so there are just those two messages. No matter what order you choose, right, it's going to be one of those two things. It's going to have to start on one side or the other, and whatever side it starts on, it's going to wind up summing out everything and getting down to that one message. And because of the fact that we've arranged things so that it always means the same thing, we're always doing the same multiple summation, it doesn't matter what order you sum things out as long as you get down to that table. Okay? What's the relationship between the message and the edge? Right. Right. So the relationship between the message and the edge, I guess it's that there are two things, right? So the edge tells you what the arguments of the message are going to be, right? It's going to be the step set associated with that edge, right? And also, it tells you what you're going to do with that message later, right? So you're going to multiply that message into the clique on one end or the other, right? So if you're passing it in that direction, you're going to multiply it into the clique on this side. If you're passing it in that direction, you multiply it into the clique on this side, right? So the edges in the junction tree are associated with the messages, and they tell us what are the arguments and how to use the messages, right? All right. More questions? Yeah.
You were saying it doesn't matter which way you do the something in. For your result, it doesn't matter, but computationally, doesn't it make a difference how you do that?
Computationally, doesn't it make a difference? So that's a good point. So all of the computational differences are going to wind up being expressed in the junction tree itself, right? So the main thing that let's see. So for computation time, right, the main thing that matters is how big a clique do you wind up having to build, right? The order of computation, so for example, round-off error could be influenced, or if you have sparsity, the time could be influenced by where you multiply in each message, right? But it's going to wind up, like if they're dense messages and you don't have to worry about round-off error, it'll give you the exact same answer in the end. And you'll just do a slightly different sequence of floating point operations to get there. But it'll be the same number of them, unless you have sparsity. Okay. Other questions? All right, so that is an insight that gets us to what's called the belief propagation algorithm. So there are all of these different elimination orders. what if I went and calculated all of the messages that any one of them could ever pass, right? And because I just showed that there's only, if there are, n edges in our junction tree, there's only going to be 2n of these possible messages, I can hopefully do that much faster than all of the possible runs of variable elimination, right? So that's the secret behind belief propagation, is that for each edge, we need 2 runs of variable elimination, one that goes in that direction and one that goes in that direction. But it turns out that with just 2 runs total of variable elimination, right, I can get all of the messages that would go over any edge in any direction. And so let's take a look at how to do that. So the way you would do that is you pick a node of the junction tree as your root arbitrarily, right? So it's an undirected tree. It doesn't matter which node I pick at root. And then I can run variable elimination in 2 different orders. The first order is going to be to start at the root and eliminate things outward until I get to the leaves, right? And, sorry. I have this backwards in the slide. What we want to do is the opposite order. So the first thing is to run variable elimination inward toward the root, right? So it doesn't matter what order as long as we eliminate every far edge before we get to the nearer ones, right? So I can pick any leaf to eliminate first, and then any leaf, and I keep eliminating leaves until I get to the root, right? And then I simulate runs of variable elimination outward from the root, right? So I'll have a bunch of incoming messages to the root, right? And I know no matter where I ran variable elimination, right? So let's pick an edge going out from the root. I have all of the messages on the incoming edge, right? Which is what I would have calculated if I had started over here and kept going, right? And so now I can just pick up this run of variable elimination right here, go eliminate outward from the root down to the leaves, right? And then any other direction leaving from the root, I can do the same thing. I take all of these incoming messages that I calculated before and pretend that I have just run a run of variable elimination, getting these incoming messages, and keep going until I get back out to the leaves. Okay? So does that make sense? Let's see. Do I have... I have an example in a couple of slides, so let's maybe it will become clearer with the example. So the idea is, now that we have all of these messages, what we want to do is be able to simulate any variable elimination order, right? So, or any order that's consistent with the tree. And the way we're going to do that is we're going to orient the junction tree edges in the direction consistent with the elimination order. In other words, if you start over on this side of the edge, then we'll send the message in that direction over the edge. And you can tell that from the elimination order. You can just read that off. And then that just selects the messages, right? We have all of these messages before. These are going to be exactly the messages that variable elimination would have computed. And we're done, right? We did no computation at this point, and we can simulate any variable elimination order. So that's kind of cool. Let's do an example, right? So so here's a junction tree, right? I'm going to make a smaller one than we've been working with so that we don't do ridiculous multiple sums on the slide. So it'll be AB, BC, CD, and CE, and CF, right? So here's our junction tree. You can check that it satisfies the running intersection property, and you can write down what the separating sets are. Whoops, I wanted to make this one EF. There. That looks enough like an E, right? So there's the separating set is E. Okay, so there's a small junction tree. These are all going to be binary variables. And I'm going to make every edge potential be the following, right? 2, 1, 1, 2, right? So that's a function with arguments true, false, true, and false, right? So that's a table of 2 arguments. So what I mean by every potential, there's a potential over AB, And its value is if A and B are both true, it'll have value 2. And if one's false and the other's true, it'll have value 1, right? So just a quick quiz for understanding. What does this junction tree do? Like, what does it mean? What are the properties of the distribution that it's trying to represent? Is it an XOR? Not quite. So XOR would be the other way around, right? So XOR would be this potential does look like a logical table. If it were 1, 0, 1, and 0, then it would be XOR, right? Any other thoughts? So is it going to be more likely for A and B to take the same value or different values? How many people think same? Okay, how many people think different? All right, good. The ayes have it. So because because 2 is bigger than 1, right? True and true is going to wind up being a more likely assignment than true and false, right? And so that's true for the pair of variables A and B. Also true for the pair of variables B and C. So what does that mean for the tree? That's right. Everything will try to align, right? Everything wants to be the same. So this is an example of what's called an associative Markov network. Associative just means that the potentials try and encourage things to be the same, right? And so, great. So basically, this is a distribution over these variables A through F, where it's going to be trying to push all of the variables to be the same, either all true or all false, but every assignment will be possible, right? It's just that the most likely single assignments will be all true and all false. Maybe another quick understanding question. If you sample from this, what do you think the probability will be that everything will be the same? Do you think it'll be 50% or higher? Or 10% or lower? People are unwilling to commit. We get maybe 2 total votes. Let's think about it this way. How many assignments are there where everything's the same? I hear 2. That's right, right? There's all true and all false. How many assignments are there where, let's say, 4 of them are true and 2 of them are false? It's going to be 6 choose 2, right? Which is 6 times 5 times 4 over 2 times 1, right? So 60, I think, right? So lots, right? So, and there's going to be even more that are evenly split. So each individual assignment where they're not quite all the same, not quite all true or not quite all false, each individual one's going to be less likely. But because there are so many more assignments that are split than that are all the same, it's still going to be more probable that you wind up getting some differences, right? All right, so that's the yeah. So, right, so we had our original Markov random field, right, which had variables A, B, C, D, E, and F, right? So there are 2 graphs going on here, right? There's the original Markov random field and the junction tree that we built from it, right? And so AB being a node means that there was a factor here, right, between A and B. There was a factor between B and C, between C and D, between C and E, and between E and F, right? So this was the original Markov random field, and we made a junction tree out of it, right? And so the nodes in the junction tree correspond to cliques in this original Markov random field, or things that will be cliques once we've eliminated some variables. And the edges here correspond to separating sets, right, which here are just one node, meaning that there's going to be a message that corresponds to node B that gets computed from this click AB and passed towards the click BC. Okay? All right, so let's do some variable elimination, right? So let's pick AB as root, right? And so the first thing we do is we pass messages inward from the leaves to the root. Oh, before I do that, actually, what I'm going to say is that we're going to now observe that D is equal to true, right? And so that means then that the potential that was originally over CD, which was 2, 1, 1, 2, is going to become a potential that's only over C and have values for true and false. The sum, the one where D is fixed to be true, right? So this first column, 2 and 1, right? So now I have a junction tree. I observed a variable. I get a smaller junction tree, right? And D is no longer really an argument. And now, OK, so we pass messages inward from the leaves to the root. So let's start with this E and F click, right? So that was 2, 1, 1, 2. We're going to sum out F, right? So F was the second argument. We'll sum across rows, right? And so the message that gets passed in this direction will just be 2 and 1. Sorry, 3 and 3, right? 2 plus 1 is 3, 1 plus 2 is 3, right? From C and D, we don't actually even have to sum across D, and so the message that gets sent will just be 2, 1, right? Because we fixed D, we observed D. From CE to C, right? So we have the potential that was 2, 1, 1, 2, but we multiplied in this potential, which is 3, 3, right? So we'll get 6, 3, 3, 6 as our potential over C and E, right? The product of all of our potentials over C and E. We sum that out, and we get a message that says 9 and 9, right? And now finally, BC, right? We had 2, 1, 1, 2, 1, 1, 2 times this potential that came in from C, so we extend it to be over B and C, which means that we just replicate it for both possible values of B, right? And then from here, right, we extended it to be 9, 9, 9, and 9, right? So we'll get, let's see, 4, 1, 2, and 2, right, when we take this. And I'm just going to write 9 times that because I don't want to have to carry around the bigger numbers, right? And then we sum that out. And again, we're summing out the C so that we get a message over B, right? And so that becomes now 5 and 4 times 9, right? And so that's the message here, 5 and 4 times 9, right? So that's going that way, and this is also going that way, right? So that's inward from the leaves to the root. Now from the root back out to the leaves, right? So let's just do a dive into the subjunctive. Suppose there had been some other node here, right? Let's just make that a little bit clearer. Suppose that there had been some other node here that was connected here, right? So I would have made this one the root, and I would have gotten a message coming out from here, right? Sorry, keep AB the root. I would have had a message coming in from here, right? So now let's think about simulating an elimination order, right? So let's simulate an elimination order that starts out here and goes out that way, right? Well, then there'll be a message coming in here. I'll multiply that in to AB, sum out, and get a message going out, right? So the interesting thing, though, is that I've already computed this message, right? And I have it hanging around because I made AB the root, and I passed messages inward to the root, right? On the other hand, suppose that I did an elimination order that moved across the graph this way, right? Well, then I would get eventually this message, multiply it into AB, sum out B, and send a message that way. And the interesting thing is I've already got that message because I passed all inward messages to the root, right? So what we have to do now is iterate over all children of the root, passing messages out in that direction, assuming that all of the messages coming in from the other directions are fixed, right? Now, in this particular example, right, there wasn't this node, and so there are no other incoming messages, so it's going to be particularly simple. But I just wanted to point out that there was that possible computation. Okay? So now from AB, right, it's going to be easy. It's this potential to 1, 1, 2. So the message going this way is 3 and 3, right? And we pass messages out this way and out that way. So passing messages this way from, it'll be 3 times 2, 1, 1, 2. So when we sum it out, it'll be 9, 9. Right? So going in this direction, I haven't left myself enough space. It's 9, 9, right? And then here, 9 times 2, 1, 1, 2, when we sum it out, right, we'll get 27 and 27. Okay? And then from here, right, the message coming in was 3, 3. We multiply by 2, 1, 1, 2, and so it'll be the same 9, 9 message, right? Which, where do I have space to write it? Maybe up here, 9 and 9. Okay, so you understand now what we've done, right? So we've simulated elimination orders that end with the root, and then simulated elimination orders that go through the root in any direction, right, leaving toward any child, right? And here there's only 2 total elimination orders because the root just had 1 child. All right? And we've got a message over every edge in every direction. And so we can use that to do something like this, right? Suppose we want the probability of A and B given that D is true, right? Meaning, so this is the sum over A of the sum over E of the probability of A, B, C, and E given D is true, right? And then using Bayes' rule, that's equal to, well, sorry, it's not Bayes' rule. It's using the definition of this probability, right? So it's sum over A and sum over E of the product of all of our potentials, right, with D fixed to be true, divided by the sum, sorry, let's do that, divided by the sum over A, B, sum over C, sum over E of the same thing. Right? Yes, I do mean that. Sorry. I want to sum out C and E, not A and E. Thank you. C, right? And then here I want to sum out everything, A, B, C, and E. Thank you for pointing that out, right? So the point is, right, I have all of these potentials. I want to sum out 2 of the variables to get the numerator, and I want to sum out 4 of the, oh, and F as well, right? Right, and so I have to sum out F, sum out F, and sum out F here, right? So the point is I want to sum out 3 variables in the numerator and 5 variables in the denominator. We know how to sum out variables. That's variable elimination, right? And so what I want to do in order to get this this marginal of the posterior, right? So the posterior is the distribution over A, B, C, E, and F when we instantiate D as true, and then we marginalize that by getting rid of C, E, and F. And in order to get that posterior marginal, I can just do 2 runs of variable elimination, right? And I've already done all possible runs of variable elimination on the previous slide, right? Here they are. And so what I can do is, okay, I want to be left with A and B, right? So A and B is this node in my junction tree. I know that whatever order I did, I would have gotten this incoming message, 5 and 4 times 9, right? And so, and then I have a local potential at A and B. And that's all the information I need, right? So I can just go back onto the next slide and take my potential, which is 5, 4 times 9, and then I want to multiply it by this potential 2, 1, 1, 2, right? So this was going back and looking at our tree, this was a potential over B, right? So that means that I want to extend it to contain A as an argument as well. 5, 4, 5, 4, right? And then 9, right? And so, right? And then this is going to be 10, 4, 5, and 8, right? Times 9. And when we sum it out, it will be, so now we're summing across rows, it'll be 14 and 13 times, oh, actually, I don't even need to sum it out, right? I didn't want the sum out, I just wanted a distribution over A and B, right? So this is my answer for the first, the numerator sum. And then for the denominator sum, I just keep going and right, sum everything out here and divide by it, right? And so I'll get this over a normalizing constant will be my probability distribution. Okay? So that makes sense to everybody? Yeah? Right, so we did, go ahead.
So if I change the condition on B,
Mm-hmm.
then I have to recompute everything?
Oh, right. So what you can do, I didn't do this, but you can go and you can do the runs of, let's see, how much can I save? Yeah, no, I'm going to wind up having to do basically everything from the beginning again if I instantiate different evidence. So once I instantiate some set of evidence, I can run message passing. If I instantiate a different set of evidence, it'll be I'll have to do another run of message passing. Right? But now I can answer any question about the posterior given this set of evidence. Right? So I could answer other questions like, if I go back here, I could ask, what is the posterior distribution over B and C, right? And so for B and C, what I would do is I would look at all of the incoming messages to this node, right? Multiply them all together then with the local potential here, and then I would get my answer. Right? Right. That's right. So you would wind up getting a much smaller set of tables in total if you conditioned on C. Yeah.
Sorry, I didn't quite follow the duration. So how did you get the three matrices at
These ones right here? Yes. Right. So these were for part of one of these computations here, right? They were the ones that led to this message, right? And so in order to send this message, right, what I have to do is, so I'm passing messages inward from the leaves to the root, right? And so I'm just doing a run of variable elimination where the root is last. So I eliminated E to get this message here. Then I eliminated I eliminated F to get this message over E here. Then I eliminated E to get this message over C here, which is 9, 9. I had a message over C here that came from conditioning on D in this potential, right? So I took the 9, 9, and I extended it to a potential over B and C instead of just B. That's this matrix here, right? I took the 2, 1, which is a factor over C, and I extended it to be over B and C, which is this matrix here, 2, 1, 2, 1, right? And then I took the local potential over B and C, which was defined to be this guy here, so I just copied that there, right? And then I took the component-wise product of all of those matrices to get that, right? And then I summed out C to get the message over B, right? So that's the general recipe for variable elimination, right? You have a bunch of messages that are coming in. They're factors that are defined over the separating sets for their corresponding edges. You have take all of the incoming messages from all but one of the directions, right? So you're passing a message out over some direction. You don't need the incoming message there. So you multiply them all together and multiply in any local potentials. Then you sum out everything except what's in the set, and that gets you a message that goes out over that edge. Okay? Right. So this is complicated. It helps to go and look at a reference. There's a reference in the previous set of slides, which is a paper by Xishang, Loliger, and Fry called Factor Graphs and the Sum Product Algorithm. That's a very nice readable paper, and it talks about not just the mechanics, but a bunch of applications from all over different areas. So I highly recommend that paper. That's right. It was, there was a link to it in the previous slides, right? So the reference, I'll just write it out again, right? Right, and it's called something like Factor Graphs and the Sum Product Algorithm. So, right, so the mechanics are pretty complicated, right? You can imagine that it would be a maybe tedious and error-prone process to write a library to do this yourself. Luckily, there are plenty of people who have already written such libraries, so that's good. The main thing is that you want to do, right, is get an understanding of what the mechanics are, right, at least at the high level, that you've made this junction tree. The goal is to calculate messages that go back and forth across the edges. Once you've got those messages, first, how big are they, right? Well, they have their tables with a number of arguments equal to the size of the set on the node or the edge, right? And what can you do with them? You can simulate any run of variable elimination that's consistent with your junction tree, right? And you do that just by collecting together all of the messages that are incoming to a, so I actually have that written out on a slide, right? So you can get the marginal over any subtree, right? So you take any subtree that you want of your junction tree. There'll be some incoming messages from the edges that go into that subtree. There'll be some factors that are local to that subtree, meaning local to one of the nodes in that subtree. And so you just multiply together all of the incoming messages and all of the local factors, and you'll get a big table whose arguments are all of the variables who are mentioned in that subtree, right? And then you can normalize that to get a distribution. And that'll be the marginal distribution, the posterior marginal distribution over that subtree. Okay? And as a special case, you can get the marginal over every clique, right? We did an example of that already. It's going to be just the product of all of the incoming messages to that node and the local potential at that node, right? Okay. And I mentioned, right, so suppose in the before, right, so we have this tree. Suppose we had wanted the posterior distribution over A and E, right? So we can't, there's no node that contains both A and E, right? The best is that we've got, let's say, this node that contains A and this node that contains E. So what we would do is we would pick a subtree, these three nodes that contains both A and E, and it'll wind up containing also B and C as well, right? And then we compute the marginal over that subtree, right, by multiplying in all of the incoming messages, one from EF and one from CD, and all of the local potentials, right? And so we'll get a table that includes some nuisance variables, B and C, and then we can sum those out afterward, right? So that points out why it is that some junction trees are better for answering some questions, right? If the question that you want to answer has arguments that are widely separated in the junction tree, you're going to wind up multiplying a bunch of stuff together that you really didn't want to have to multiply together, right? So the best answer then might be to build a junction tree, or it might be to bite the bullet and build a big table and sum out the things that you want, depending on sort of how far apart they are. All right, so that's the junction tree algorithm. Okay, as I pointed out, it is a little bit complicated. You'll get an opportunity to practice it but the reading, the Shishang et al. Reading is a good source. So any more questions about the algorithm? Yeah.
Each time I change the condition, I have to recalculate everything.
That's right.
But if I use like, since these are just tables potential,
Mm-hmm.
if I use symbolic and calculate all the messages and just put like, at the end whenever I'm putting condition, just put 1 and 0 for
Right, so you could do symbolic computation to get an analytic expression for one of the messages, and that expression would tell you essentially the computations you would need to do in variable elimination to get that message, right? So you don't actually, if you do it symbolically, there's no savings, right? The junction tree is essentially already a symbolic representation of the expression that you need to calculate. Right? I guess the other thing is if you change evidence somewhere in the tree, you might not need to change all messages, right? It might be that you only need to change some fraction, and then by the time you get somewhere, like some of the messages will be the same, and you don't need to recalculate anything from that point on, right? So you could get that. But in general, you might have to change, a good fraction of it. Okay. So let's see. There's just a few more things that I wanted to mention. Right, so it was easy for us after belief propagation to get all of the clique marginals and also all of the marginals over separating sets, right? Because the separating set is a subset of the clique on either side of it, and so you can just sum out from either of those cliques, and you better get the same answer, right? Because it's the same distribution. So by Bayes' rule, you can ask for the probability of all of the variables that are in a particular clique that are not in one of its subsets, right? The subset, on some edge, right? Conditioned on the variables in the separating set. And that is, by Bayes' rule, is just probability of the union of the clique and the union of clique minus subset and subset, which is just the clique, right? Divided by the probability of the subset. Right? So we can get conditional probabilities as well, right, for cliques. We can get marginals easily. We can also get conditionals for cliques conditioned on subsets. And now suppose that we have an edge, right, that's like clique 1 to clique 2 with a subset on it here, right? Well, that'll be, by Bayes' rule, P of clique 1 times P of clique 2 given clique 1, right, which is equal to P of clique 1 times P of clique 2. Right, so this here, right, conditioning on clique 1 is exactly the same as conditioning on subset, right? And so we divide by P of subset, right? And the reason that's true, right, is that we know that clique 2 is independent of all of the other variables in clique 1 given the subset, right? So that's interesting, right? We can get joint probabilities of two cliques by multiplying the probability of each of the cliques and dividing by the by the marginal over the subset. Okay? And so we can continue the same process over the entire tree, and the probability of everything is going to be the product over clique I of P of this is union, right? The joint probability of the two cliques. So this is Bayes' rule, right? So the probability of the joint probability of C1 and C2 together is you can get by taking the product of the probabilities of C1 and the conditional probability of C2 given C1. So that's an expression for the joint probability of C1 and C2 together, which is the union. No. So this is a probability table over all of the variables in both of these cliques, right? So, I see what you're talking about, right? So any individual element of this will correspond to the and of some event relative to clique 1 and another event relative to clique 2, right? So the individual elements of this table correspond to logical ands. But this is the argument set of the table. And so the argument set is the union of the two cliques. Maybe I can say that again, right? So what I'm asking for, so I could have two cliques, A, B, C, and B, C, D, right, that are connected by the separating set B, C, right? And so what I want is the joint probability over A, B, C, and D, right? And this is equal to the probability of A, B, C times the probability of B, C, D given A, B, C, right? So the joint probability over all of A, B, C, and D is equal to the probability of A, B, C times the conditional probability of B, C, and D given A, B, and C. And that's equal to P of B, C, D given B and C, right? So I guess I should just cross out, right? So, yeah, right. So given B and C, we'll be fixing those arguments, but right. So, but this is the Bayes rule, right? The Bayes rule is you have a large thing, right? So I guess here, right, these guys are essentially useless, so I'll just cross them out, right? So it's P of ABC times P of D given ABC, and that's equal to P of D given BC, because there's no direct connection in this graph from A to D without going through B and C. Okay, and so the probability over the union of everything, right, like this, is well, I can write it like this, right, because this I've written already as this ratio. Okay. So the probability over everything is going to wind up being right. If I just do this same trick over the entire tree, it's going to be, you can write it as that ratio. You multiply together all of the marginal probabilities over cliques, and you divide out all of the marginal probabilities over separating sets. Okay, and that gets you the joint distribution over everything. So that's a once we've done this calculation, gotten all of the clique and subset marginals, it's called a calibrated junction tree. And calibrated junction trees are nice because they are essentially, you can think of them as a factor graph where the factors are basically joint probability tables, right? So either a joint probability table over a clique or the reciprocal of a joint probability table over a subset. Right? So that's just another useful representation that you might wind up needing to do some calculation. Just the last couple of things that I wanted to mention before we are done with graphical models. The factors that I've been working with so far are what I would call soft factors. They don't have any zeros in them. You can also write hard factors that have some zeros in them, right? And here you can think of this as a hard constraint, right? X and Y are not allowed to jointly take the value, let's say 0 and 1, right? Whereas here, this is just sort of a soft constraint where we prefer not to have them take that value, right? And basically, the only thing to remember about hard factors is that they can lead to some complications, right? So for example, you could write down a graphical model that corresponds to not a number, right, if it's impossible to satisfy all of your hard constraints. And so trying to do calculations with it would lead only to heartbreak, right? Because you'll never, it doesn't represent a continuous distribution. And so you might be able to do some calculation on a part of it, but it would be meaningless because the whole thing corresponded to a non-existent distribution. The other thing is that conditional independences wind up getting a little weirder when you have hard factors. And if you're interested, take a look at the Kohler et al., the Kohler book. Look up Hammersley-Clifford in the index. So basically, soft factors nice, hard factors can be annoying. I mentioned last time this idea of moralizing and triangulating, right? So I don't want to go into that in much more detail. This is just the algorithm that goes by that name. And it's an alternate way to build a junction tree, right? To me, it's more difficult to understand, but you might want to look at it. If this one is easier to understand for you, you can take a look at that algorithm as well. Continuous variables, right? So we've been working with discrete variables. Graphical models can have perfectly well continuous variables as well. So instead of conditional probability tables, we'd have conditional probability densities or conditional probability measures to deal with continuous variables. Instead of tables of potentials, we'd have potential functions, right? So instead of having rows correspond to one variable and columns correspond to another variable, you'd have a function with two arguments, right? And that would be your potential. Okay. And same thing with messages. Instead of tables, you get functions. And everywhere that there was a sum in the variable elimination algorithm, you replace it by an integral. And if you just go back over the slides, replacing all sums by integrals, you get all of the appropriate algorithms for dealing with continuous variables. Now, there is a fly in the ointment that functions are infinitely large objects, and so it might be kind of a pain to represent them. And yes, in fact, it is. But we can represent them any way we want. So I've seen people do it as mixtures of Gaussians. I've seen people do it approximately by representing them as sets of samples. You could have a Gaussian process that represented your message. And when we get to exponential families, you can use exponential family distributions. I also wanted to mention this thing called Loopy belief propagation, right? So suppose that we have a graph that sort of locally looks like a junction tree, right? So A, B, C, A, B, D, B, D, and E, and let's say B, A, and E and F, right? So something like that. These guys, and connect them like this, right? So this is not a junction tree. But locally, it can kind of look like a junction tree, right? So if I delete this edge, right, then there's sort of a nice junction tree here, right? And if I delete, basically I can look in the neighborhood of, let's say, this node, right? And it has two neighbors with a subset there, right? Right, and so I could like focus on this node, take just these two neighbors, think of them as a piece of a junction tree, and calculate a message that went across this node from this factor, from this message to compute that message, right? And same thing, I could focus on this guy, compute messages that went across. And these messages might not be correct, right? They might not represent anything useful. But I can still apply the algorithm, right? Like I can run the code locally. I have an incoming message. I have local factors. I can multiply them together and sum things out to get outgoing messages, right? And so you could have the idea of, well, let's just do that, right? I pick a node. I start with some message labels in both directions across every edge. I pick a node. I pick which messages are going to be incoming and which one's going to be outgoing. And I do the message calculation and update the outgoing message, right? And then I pick another node and another outgoing edge, calculate the message that goes across that edge, right? Seems kind of crazy, but surprisingly, it actually works really well in some situations, right? And so this is called loopy belief propagation, loopy because it's on a graph with loops. And again, the Xishang reference has some examples where this is a really good algorithm. In particular, decoding a certain class of error-correcting codes, this turns out to be one of the best known algorithms for it, right? So loopy belief propagation, I'm only mentioning it briefly because there's not much to say about it, right? Same code that you already know from belief propagation. No theoretical guarantees that I know of, but for some unknown reason, it actually works really well, right? In some cases, not in all of them. It can also go horribly wrong. So you've been warned, yeah.
So there are somewhat weak guarantees for special graphs.
Right.
First of all, your cell phone is actually using loopy belief propagation.
Right.
Or at least some version of it. It's called turbo code.
Right. That's what I mentioned for the error-correcting codes.
This is essentially what was quite a revolution in terms of data compression. And the other thing is under certain assumptions on the properties of potential. So for instance, if they don't couple things too much,
Mm-hmm.
and if your chain is long enough and you don't have too many loops, then you can actually get some guarantees.
Right.
So for instance, there's the work of Alex Tyler,
Mm-hmm.
where he showed that if the total variation in the click potentials is bounded, things are okay. There are actually corresponding inference algorithms that use this. So Graphical effectively uses this by saying, well, okay, if the inference is bounded, I might as well get away with just doing inference locally, and everything's going to be fine. And then they essentially, after the fact, say, hey, I'm converged, so therefore it must be okay.
Right.
Okay, they do a little bit more detail, but that's
Right.
sort of the idea.
Right. I should have said maybe to a first approximation, the theory is absent. But there are definitely some interesting cases where there is theory. GraphLab is a great example. The turbo decoding is another great example. Maybe the most famous example is the turbo decoding. Okay. So that's loopy belief propagation. And then I also wanted to mention plate models, right? So a plate model is something that looks like this, right? So you'll have a variable y, you'll have some variables xi for I equals 1 to n, right? There, like that. Every one of those variables xi has some particular structure, right? And so what this is called a plate model, and the square plate corresponds to basically a macro for constructing a piece of your network, right? So what this corresponds to is that you have a network that's y, x1, x2, x3, right? If n is 3, right? And they all look like that, right? And so this graphical model says that y is a child of all of the x's, right? Or if you had it the other way around, y could influence all of the xi's, right? And you could have a plate like that. Right? And so this graphical model is one that you've seen before. Does anybody recognize it? It's kind of a naive graphical model. Right? So this is the naive Bayes model, right? So it's the class variable y influences all of the observed variables x, and the observed variables x are conditionally independent given y, right? And so if you do the Bayes net, right, x1, x2, x3, right, like that, this, and look at the conditional independences that you can read off of this Bayes net, it says exactly what the naive Bayes assumptions are, right? That you have conditional independence of the observables given the class variable. Okay. So plate models, they're effectively a macro language for constructing huge graphical models, right? So you could have something where you have, you know, let's say observable with xi and j, right? And you could have two intersecting plates on top of xi and j, right? I equals 1 to n, right? Like that. And another plate like that, right? That says now that j is equals 1 to m, right? And so now this node xij is inside two nested for loops, right? So there's going to be n times m of them. And, you know, let's say, you know, maybe ui, right, is inside here, influencing xij, and, you know, vj is in here influencing xij, right? And so if I write out something like that, I'll have a grid of x nodes. I'll have, so these are the x's. I'll have, you know, rows and columns, right? So these are the u's, and then there are v's on the rows, right, like that. Let's just, right, so these are v's, right? And you'll have, for example, that the first u and the first v will influence the first x. The first u and the second v will influence that guy, right? And I'm not going to keep drawing it out because it would get to be a mess of spaghetti, but you get the idea, right? And so it's a really good way to make graphical models that are too huge for you to do anything with, at least to do anything exact with, but it's a nice sort of shorthand for describing large graphical models. And you'll see a lot of examples of this in machine learning papers. For example, if you go look up the paper on latent Dirichlet allocation, right? Or any paper that is about latent Dirichlet allocation, they all have this one figure, which is the plate model that describes LDA, right? And there's not a lot to say about it other than that, well, macro languages are clearly useful for describing big Bayes nets. And there are other macro languages as well. For example, Markov logic networks can be thought of as a macro language for describing big undirected graphical models. And independent choice logic is another good example of a macro language. It looks more like a logical expression, right? So yeah, plate models plus loopy belief propagation equals a large number of machine learning papers, right? If you know both of the technologies and you apply them to a new thing, there was a time when every time you did that, it led to a new paper. I think we're out of those times now, but it's a useful tool to know about. So I think that next time, so this is the end of graphical models, at least in this form. Next time we're going to move to exponential families of distributions. All right. Any more questions? All right, great. I'll see you guys next time.